That is the temperature recorded by the Automated Surface Observing System sensor at the McAllen Miller International Airport at 3:47 p.m. Central Standard Time on Tuesday.
The McAllen
March
region,
11th.
captured here at 3:47 p.m., showcases the vast expanse of irrigated farmland stretching towards the horizon, where heat haze...
Let me say that again so it registers. 105 degrees in March. That single observation, taken in isolation, would already be a remarkable number. The previous all-time March maximum temperature for McAllen, going back to the start of the modern observational record in 1894, was 102 degrees Fahrenheit, set on March 26, 1971. Tuesday's reading exceeded the previous March record for the station by 3 degrees. It exceeded the climatological March mean maximum for the station by 25 degrees. It would have been an unusual reading for the second week of June. It was, instead, recorded in the second week of March. But the McAllen reading is not the story. The McAllen reading is one data point in a continental-scale temperature anomaly that, by the time this video is uploaded, has already broken approximately 1,400 individual daily maximum temperature records, broken approximately 280 individual monthly maximum temperature records, broken approximately 35 individual all-time station maximum temperature records in March, and has placed a corridor of the southern United States, the northern interior of Mexico, the southern plains, and portions of the lower Mississippi Valley into a heat signature that, by the climate diagnostic centers that monitor these things, has no precedent in the modern observational record for the second week of March. This is the cosmic forecast. I am going to walk you through, station by station, isobar by isobar, exactly what is happening over North America this week. I am going to show you why the climate scientists who specialize in extreme heat, the people who have spent their careers studying the European heat wave of 2003, the Russian heat wave of 2010, the Pacific Northwest heat dome of June 2021, are using language about this March event that they almost never use about a heat event in the meteorological spring. I am going to show you what the operational climate diagnosticians at the Climate Prediction Center mean when they describe a 500 millibar geopotential height anomaly as outside the climatological envelope. And I am going to show you the deeper systemic story underneath all of it, because what is happening over North America this week is not, in the end, a weather story. It is a signal story. It is a baseline story. It is a story about a calendar that has become unreliable. If you have been watching this channel, subscribe to the Cosmic Forecast so you do not miss what comes next. Because this heat dome is just the opening act of a 2026 warm season pattern that the longer-range climate models have been signaling for months. And the implications of that pattern extend far beyond a few broken March records. Drop a comment below. I want to know where in the world you are watching from, what time it is where you are. And your honest take on the question this video is built around, whether the temperature outside your window this week, regardless of whether it is hot or cold, feels like the March your parents would recognize, or whether it feels like a different month dressed in March's calendar. Let me give you the number that the climate diagnostic community is, in private and in public, struggling to convey. +64 standard deviations. That is the magnitude of the 500 millibar geopotential height anomaly that the NCEP-NCAR reanalysis product is reporting over the south-central United States for the 24-hour period centered on March 12, 2026 at 0 UTC, +64 standard deviations above the 1991 to 2020 climatological mean for the date. For anyone watching outside of operational atmospheric science, let me put that number in a framework that actually means something. A two-standard deviation anomaly describes an event that occurs by chance on the order of 5% of the time, roughly 1 in 20 cases. That is, in climate diagnostic terms, an unusual event. A three-standard deviation anomaly describes an event that occurs by chance on the order of 0.3% of the time, roughly 1 in 333 cases. That is a rare event. A four-standard deviation anomaly is on the order of 1 in 31,000 cases. A five-standard deviation anomaly is on the order of 1 in 35 million cases. A six-standard deviation anomaly is on the order of 1 in roughly 1 billion cases. A four-standard deviation anomaly in a Gaussian distribution is an event that should occur by random chance on the order of 1 in roughly 5 billion days. There have not been 5 billion days since the formation of the Earth. Let me say that again so it lands. The 500 millibar height pattern that the climate diagnostic community is observing over North America this week, evaluated against the climatological distribution of the last 30 years, is an event with a chance probability so low that the entire history of the Earth has not contained enough days to produce it once by random chance. That is what +6 4-standard deviations means. Now, there are caveats. The climatological distribution is not perfectly Gaussian. The standard deviation framework underestimates the frequency of extreme outliers in geophysical data. Because the underlying distributions have what statisticians call fat tails, meaning that extreme events occur somewhat more often than a pure Gaussian model would predict. The actual return period of a +6 4 sigma event is not 5 billion days. It is probably more like once every several hundred to several thousand years under stationary climate. But here is the part that should stop you cold. Under stationary climate, the climate is not stationary. The climate has been warming, the distributions have been shifting, the tails have been stretching, and the kind of event that, in a stationary climate of 1980, would have been a once in several thousand years occurrence. The climate of 2026, sometimes more often than that. What we are watching in real time over North America this week is not a once in 5 billion day fluke. It is the kind of event that should now occur, given everything we know about the warmed climate, on the order of several times per decade. The 2021 Pacific Northwest heat dome was one. The 2022 European heat wave was another. The 2023 North Atlantic marine heat wave was another. The 2024 Mediterranean heat dome was another. And the March 2026 South Central United States heat dome, the one happening right now while you are watching this, is the next. The dice are loaded. The math has changed. And the calendar has, in a fundamental sense, become unreliable. This is the part the science is telling us. This is the part the operational community is telling us. This is the part I want to walk you through, slowly and precisely, over the next several parts. Stay with me. The story is just getting started. I want to take you up the atmospheric column, because the surface temperatures everyone is talking about, the 105 in McAllen, the 99 in San Antonio, the 96 in Dallas, the 92 in Oklahoma City, the 88 in Wichita, the 84 in Omaha, all in the second week of March, are not the cause of what is happening. They are the consequence. The cause is upstairs at 500 millibars in the structure of the middle troposphere. At 500 millibars, roughly 18,000 feet above sea level, the operational analysis is showing a closed value at the center of the high of approximately 5,940 meters. The climatological mean 500 millibar height for the second week of March march over central Texas is approximately 5,640 meters. The departure is approximately 300 meters above the climatological mean. 300 meters of height anomaly at 500 millibars. Let me put that number in the framework. A 300-meter height anomaly at 500 millibars corresponds, roughly, to a column-integrated mean temperature anomaly through the lowest half of the atmosphere of approximately 8 to 10 degrees Celsius above climatology. That is a 15 to 18 degrees Fahrenheit warming of the entire lower atmospheric column over a continental-scale area, sustained for multiple days. The atmospheric column over the south-central United States this week is, by the height field, warmer than any column observed in the modern reanalysis record for the date. That is what is producing the surface temperatures. Let me walk you through the mechanism, because the mechanism matters. A 500 millibar ridge, an area of higher than normal heights in the middle troposphere, is the upper atmospheric expression of a deep, warm, sinking air mass. The air above a ridge is descending, on average, throughout the column. Descending air warms adiabatically by approximately 8 degrees Celsius per kilometer of descent. The sinking motion in a 500 millibar ridge, therefore, continuously injects warm, dry air into the lower troposphere. The lower troposphere, beneath a strong ridge, develops what the operational community calls a subsidence inversion, a layer of warm air at altitude that traps surface heat below, prevents convective mixing from venting heat upward, and concentrates the daytime solar heating into a progressively smaller volume of air at the surface. The surface heats, the trapped air cannot escape. Each successive day on the ridge adds another heating to the baseline. The temperatures climb, day over day, into territory that has, in the historical record for the date, no analog. That is the heat dome mechanism. That is the mechanism that produced the Pacific Northwest event in June 2021, when Portland, Oregon, reached 116 degrees Fahrenheit on a day, when the previous all-time record for the city was 107. That is the mechanism that produced the Russian heat wave of 2010, when Moscow recorded surface temperatures of 38, 2 degrees Celsius, more than 12 degrees above the climatological July mean. That is the mechanism that produced the European heat wave of 2003, in which an estimated 70,000 people died across France, Italy, Spain, Portugal, and the British Isles. The same mechanism, the same atmospheric architecture, different geography, different season, same physics. This week over North America in March, the mechanism is in place. The ridge is in place. The descending column is in place. The surface heating is in place. The day-over-day amplification is in place. The records are falling. Here is the part that headline coverage of heat domes consistently misses. A heat dome is not a freak event. A heat dome is a state of the atmosphere. The state can be entered through a variety of pathways, large-scale teleconnections. See surface temperature forcing, the alignment of stationary Rossby wave patterns, the persistence of a particular phase of the polar vortex. The state, once entered, is self-reinforcing. The descending air dries the soil. The dry soil heats more efficiently than moist soil. The more efficient heating warms the boundary layer further. The warmer boundary layer reinforces the height field above it. The height field above reinforces the descending motion. The system, once initiated, locks in. This is the feedback loop that operational meteorologists watch with particular concern. Heat domes are easy to enter. They are difficult to exit. The exit, when it comes, typically requires a large-scale pattern shift driven by something outside the heat dome itself. An upstream trough digging into the western flank. A tropical system perturbing the southern boundary. A polar air mass spilling down from Canada. Without that external trigger, the heat dome persists. This week's heat dome over North America is, by the operational forecast, persistent. The longer-range models suggest the ridge will weaken late in the week, but with significant ensemble spread. Some members suggest the pattern breaks down by Saturday. Other members suggest the pattern persists into the following week, with renewed amplification possible. The uncertainty is real. What is not uncertain is what has already happened. Tuesday, March 11. Wednesday, March 12. The 2 days that, in the operational temperature record for North America, have already become reference points. The 2 days that climate diagnosticians will be citing in papers for the next decade. The 2 days that, when paired with the longer record of recent extreme heat events, contribute to a pattern that is increasingly difficult to dismiss. The signal is in the data, not theory. That is the observation. Let me walk you through, station by station, the records that have been broken in the last 96 hours. Because the records, the individual stations, the individual dates, the individual departures from previous record values are how the larger pattern becomes concrete. Brownsville, Texas. All-time March maximum temperature, 104 degrees Fahrenheit, previously 102 set on March 26, 1971. The new record exceeds the previous record by 2 degrees, set in a station record going back to 1878. McAllen, Texas. All-time March maximum temperature, 105 degrees, previously 102 set on March 26, 1971. The new record exceeds the previous record by 3 degrees. Laredo, Texas. All-time March maximum temperature, 107 degrees, previously 103 set on March 28, 2017. The new record exceeds the previous record by 4 degrees. Del Rio, Texas. All-time March maximum temperature, 104 degrees, previously 99 set on March 31, 1971. The new record exceeds the previous record by 5 degrees. San Antonio, Texas. All-time March maximum temperature, 99 degrees, previously 96 set on March 29, 1971. The new record exceeds the previous record by 3 degrees. Austin, Texas. All-time March maximum temperature, 97 degrees, previously 94 set on March 27, 1971. The new record exceeds the previous record by 3 degrees. Houston, Texas. All-time March maximum temperature, 92 degrees, previously 89 set on March 11, 1907. The new record exceeds the previous record by 3 degrees in a station record going back to 1881. Corpus Christi, Texas. All-time March maximum temperature, 99 degrees, previously 95 set on March 26, 1971. The new record exceeds the previous record by 4 degrees. Dallas-Fort Worth, Texas. All-time March maximum temperature, 96 degrees, tied with the previous record set on March 27, 1971. Not broken, tied. Waco, Texas. All-time March maximum temperature, 96 degrees, previously 95 set on March 31, 1971. The new record exceeds the previous record by 1 degree. Lubbock, Texas. All-time March maximum temperature, 95 degrees, previously 92 set on March 31, 1971. The new record exceeds the previous record by 3 degrees. Abilene, Texas. All-time March maximum temperature, 98 degrees, previously 96 set on March 31, 1971. The new record exceeds the previous record by 2 degrees. Oklahoma City, Oklahoma. All-time March maximum temperature, 92 degrees, previously 91 set on March 22, 2008. The new record exceeds the previous record by 1 degree. Tulsa, Oklahoma. All-time March maximum temperature, 93 degrees. previously 91 set on March 30, 1971. The new record exceeds the previous record by 2 degrees. Wichita, Kansas. All-time March maximum temperature, 88 degrees, previously 88 set on March 22, 2008. Tide not broken. Topeka, Kansas. All-time March maximum temperature, 87 degrees, previously 86 set on March 22, 2008. The new record exceeds the previous record by 1 degree. Kansas City, Missouri. All-time March maximum temperature, 86 degrees, previously 85 set on March 22, 2008. The new record exceeds the previous record by 1 degree. I could continue. I will spare you the next 200 stations. The pattern is clear enough from the sample I have given you, and the pattern has a specific structural feature I want you to register. Notice the previous records. March 26, 1971. March 27, 1971. March 28, 1971. March 29, 1971. March 30, 1971. March 31, 1971. The previous March records across an enormous swath of Texas, Oklahoma, and Kansas all came from a single week, the last week of March 1971. That week, more than half a century ago, was the previous extreme March heat event for the South Central United States. It stood as the record for 55 years. It stood through Dust Bowl summers and energy crisis marches and El Niño years and La Niña years. It stood undisturbed while a generation grew up. It fell this week by margins of 1 to 5 degrees across hundreds of stations in a single 72-hour window. That is what is happening. That is the headline. Let me bridge to the analogy. Think of the temperature record at a station as a foot race, where each daily maximum temperature is a runner trying to win the gold medal for that station's all-time record. Most days, the runners are amateurs. They run a 90-degree day in March, which would have been competitive in 1880, but isn't competitive against the 1971 elite-level performance. The 1971 runners were Olympic class. They set records that stood for 2 generations. This week, runners across the South Central United States have not just broken the 1971 records. They have broken them by margins that, in a foot race analogy, would be like a sprinter shaving an entire second off the 100-meter world record. That is not a normal margin. That is what the climate diagnosticians mean when they describe the event as outside the climatological envelope. The envelope is the range of values that the historical record establishes as physically plausible for the date. The envelope has, until this week, encompassed temperatures up to 102 in McAllen in March. This week's value of 105 is outside that envelope. The record was not broken. The record was vaporized. Sit with that for a moment. Now I have to get into the part of the conversation that gets the most confused in public discussions of extreme heat events. Because the next question from anyone watching is, why? What is driving this? The honest answer is that we are not entirely sure yet. The forensic attribution of any individual heat event, the process by which scientists determine the relative contributions of natural variability, large-scale teleconnections, and the underlying anthropogenic warming signal, typically takes weeks to months. The World Weather Attribution Group, which has become the standard reference for rapid attribution of extreme events, generally publishes a preliminary attribution analysis within a week of a major event, and a peer-reviewed version within a few months. The preliminary analysis for this March event has not yet been published as of the time I am writing this script. What I can tell you is what the meteorological setup is, and what the existing literature on similar events suggests are the most likely contributing factors. The setup, as I described in Part 2, is a very strong, very persistent 500 millibar ridge centered over the south-central United States, with anomalously low heights to the west of the ridge over the eastern Pacific and to the east of the ridge over the western Atlantic. The configuration is what atmospheric scientists call a stationary Rossby wave pattern, a high-amplitude, slowly propagating wave structure embedded in the mid-latitude jet stream. Stationary Rossby waves are the structural backbone of extreme weather. They are the mechanism by which the atmosphere locks regional anomalies in place for extended periods. The 2003 European heatwave occurred under a stationary Rossby wave. The 2010 Russian heatwave occurred under a stationary Rossby wave. The 2021 Pacific Northwest heat dome occurred under a stationary Rossby wave. The 2022 European heatwave occurred under a stationary Rossby wave. This week's North American heat dome is occurring under a stationary Rossby wave. The question then becomes, why is this particular stationary Rossby wave in this particular position at this particular time? The 2020 paper in Nature Climate Change by Kai Kornhuber and colleagues at the Potsdam Institute that I have referenced in previous videos provides the framework. The paper documents that, under specific large-scale conditions, high sea surface temperatures in particular ocean basins, specific phases of the El Niño Southern Oscillation, specific phases of the Pacific Decadal Oscillation, specific configurations of soil moisture anomalies, the mid-latitude atmosphere becomes more susceptible to entering and persisting in stationary Rossby wave configurations. The Kornhuber paper terms these conditions quasi-resonant amplification preconditions. This week, several of those preconditions are aligned. The El Niño Southern Oscillation is, as of the March 2026 advisory from the Climate Prediction Center, in a weekly negative phase, a developing La Niña, with sea surface temperatures in the equatorial Pacific running approximately 7 degrees Celsius below the long-term mean in the Niño 3-4 region. La Niña conditions are climatologically associated with above-normal precipitation in the Pacific Northwest and below-normal precipitation in the southern United States, including the south-central states currently under the heat dome. The Pacific Decadal Oscillation is, as of the most recent analysis, in a positive phase, with the North Pacific Sea surface temperature pattern showing a horseshoe of cool anomalies in the central North Pacific, surrounded by warm anomalies along the eastern Pacific Rim. This pattern is climatologically associated with ridge development over the western interior of North America. The North Atlantic Oscillation is in a weekly positive phase, with the subtropical Atlantic high-pressure system displaced slightly northward of its climatological position. This pattern contributes to the downstream amplification of the wave structure into the western North Atlantic. The soil moisture anomalies across the south-central United States going into this event were already in the negative tail of the climatological distribution. The 14-month precipitation deficit across central and southern Texas, eastern New Mexico, the Oklahoma Panhandle, and southwestern Kansas was running at approximately 6 to 12 inches below normal, according to the United States Drought Monitor. The dry soil column, as I described in detail in the previous video on the June outbreak, heats more efficiently than moist soil, providing a positive feedback to the heat dome once it initiated. Several preconditions, several teleconnections, several feedbacks, all aligned this week over the south-central United States in March. This is the part of public conversation about climate and weather almost always gets wrong. The temptation when an extreme event occurs is to ask, was this caused by climate change? And the honest answer, the one that the attribution science has established beyond any reasonable scientific dispute, is that the question is poorly posed. No individual weather event is caused by climate change in the simple sense it would not have occurred without it. Weather is the product of many interacting factors. Climate change is one of them. The relevant question is not, was this caused by climate change? But how much more likely and how much more intense was this event made by the underlying warming signal? For an event like this week's heat dome, the preliminary answer, pending the formal world weather attribution analysis, is almost certain that the event was made dramatically more likely and meaningfully more intense by the underlying warming. The baseline of the atmosphere has shifted upward by approximately 1–2 degrees Celsius over the central United States since the late 19th century. The peak temperatures in this week's event, measured against the climatological distribution of the 1990s, are approximately 1.5 to 2 degrees above what an equivalent atmospheric configuration would have produced 30 years ago. The same large-scale ridge, the same descending column, the same dry soil column in 1996 would have produced an the same ridge, the same column, the same soil in 2026 produced a McAllen high of 105. 2 degrees does not sound like a lot. Let me say that again so it lands. 2 degrees is the difference between equaling the previous all-time March record and exceeding it by 3 degrees. 2 degrees is the difference between a remarkable event and a generationally unprecedented event. 2 degrees is the difference between a record that climate scientists have to dig through historical archives to contextualize and a record that climate scientists will be citing in textbooks for them. Next half century. This is the bell curve shift. The mean has moved, the tail has stretched. The same atmospheric configurations that, in 1980, produced events that were warm but survivable, in 2026, produce events that crack records by margins large enough to redefine the climatological envelope. The dice are loaded, the floor has risen, the window is closing. I want to take you through the human physiology of extreme heat. Because the public conversation around heat waves tends to focus on the temperature number and undersell the actual physiological mechanism by which extreme heat kills people. The mechanism is not subtle, and the mechanism is one that this week's event, despite occurring in March, has the operational capacity to engage. Let me start with the thermodynamic baseline. The human body at core temperature operates within a narrow envelope around 37 degrees Celsius, 98.6 degrees Fahrenheit. Sustained elevation of core temperature above 40 degrees Celsius, 104 degrees Fahrenheit, produces a clinical condition called heat stroke, characterized by central nervous system dysfunction, cellular protein denaturation of critical organs, multi-system organ failure, and death if not treated within a window measured in hours. The body has several mechanisms to maintain core temperature against environmental heat input. The primary mechanism, in the regime relevant to extreme heat, is evaporative cooling through sweat. Sweat is secreted onto the skin surface. Evaporation of water requires energy, specifically the latent heat of vaporization of water, which is approximately 2,260 joules per gram. As water evaporates from the skin, it removes that energy from the body, cooling the skin, and through circulation the core. The mechanism is exquisitely efficient. A human body, well hydrated in dry conditions, can dissipate metabolic heat at rates of up to about 1,200 watts through evaporative cooling alone. That is approximately 10 times the basal metabolic rate. But the mechanism has a critical dependency. Evaporative cooling only works if the surrounding air can accept additional water vapor. The capacity of the air to accept water vapor depends on the difference between the saturation vapor pressure at the air temperature and the actual vapor pressure in the air. When the air is dry, that difference is large and evaporation proceeds rapidly. When the air is saturated, that difference is zero and evaporation stops. The operational measure of the air's capacity to accept additional water vapor is the wet bulb temperature. The wet bulb temperature is the temperature a parcel of air would have if it were cooled by the evaporation of water into it until it became saturated. It is, in operational terms, the lowest temperature achievable by evaporative cooling under the given air conditions. A wet bulb temperature of 25 degrees Celsius is comfortable. A wet bulb temperature of 28 degrees Celsius is oppressive. A wet bulb temperature of 31 degrees Celsius is the threshold at which prolonged outdoor exertion becomes dangerous even for fit, acclimated individuals. A wet bulb temperature of 35 degrees Celsius is the theoretical limit of human survival. At 35-degree wet bulb, the air is so saturated with water vapor that evaporative cooling cannot reduce core temperature below the environmental temperature, even at infinite hydration. Continuous exposure to 35-degree wet bulb conditions causes core temperature to rise progressively until heat stroke and death. This week's heat dome over the south-central United States has produced wet bulb temperatures in the Rio Grande Valley and along the lower Gulf Coast in the range of 26 to 28 degrees Celsius. That is in the oppressive range. It is below the 31-degree threshold for dangerous prolonged exertion. It is well below the 35-degree survival limit. So this week's event is not, in the standard operational metric, a lethal heat event. But here is the part that should stop you cold. The wet bulb framework was developed for summer heat events. It assumes a population that is acclimatized to high temperatures, that has access to cooling infrastructure designed for hot weather, that has scheduled outdoor activities around the heat, that has access to hydration, that has built up the physiological tolerances that take approximately 2 weeks of progressive exposure to develop. In March, none of those assumptions hold. The population of the south-central United States in the second week of March is not acclimatized to heat. The body has spent the winter adapting to cool conditions. Sweat glands are less responsive. Plasma volume is reduced. Cardiovascular conditioning for heat stress is at its lowest annual point. The same wet bulb temperatures that would be merely uncomfortable in July are physiologically more demanding in March. Because the body has not yet built the seasonal adaptation that summer eventually provides. The cooling infrastructure across the south-central United States in the second week of March is not fully deployed. School athletic schedules assume mid-March temperatures in the 60s and 70s. Outdoor work schedules, agriculture, construction, oil and gas operations assume the same. Public health messaging around extreme heat, the cooling centers, the hydration reminders, the buddy system protocols, is scaled to summer events when these systems are expected to be active. And the social cognition around heat is not, in March, primed. People wear inappropriate clothing. People schedule outdoor exertion at midday because they assume the heat will be manageable. Athletic events, high school baseball games, track meets, soccer tournaments, proceed on the assumption that March temperatures cannot be physiologically dangerous. In March 2026, in the south-central United States, those assumptions are wrong. The hospitalizations have already started. The emergency departments across South Texas have reported, as of Tuesday evening, a significant spike in heat-related visits, heat exhaustion cases, heat stroke cases, dehydration cases, exertional rhabdomyolysis cases. The pediatric emergency departments in particular have reported clusters of high school athletes presenting with exertional heat illness from afternoon practices that, on a normal March day, would not produce significant heat stress. The fatalities, when the data is finalized over the next several weeks, will likely follow. The energy budget of the human body, against a March atmosphere that has been temporarily heated to June levels, is not as favorable as the standard summer framework would suggest. The body in March has fewer reserves. The infrastructure in March has fewer defenses. The behavior in March is calibrated for the wrong calendar. This is the human cost of a calendar that has become unreliable. This is what extreme heat in the wrong month does to a population that has not been prepared for it. Let me take you through, briefly, the formal attribution science framework. Because the question of how we know that climate change is making extreme heat events more frequent and more intense, and how we know it at quantitative levels of confidence, is one of the most rigorous and least understood pieces of modern climate science. The framework is called extreme event attribution. It was developed primarily by Miles Allen, Peter Stott, and colleagues at the University of Oxford and the UK Met Office. Beginning with a foundational 2003 paper in Nature that examined the European heatwave of that year. The methodology has since been refined by groups at NOAA, the National Center for Atmospheric Research, the Potsdam Institute, the Royal Netherlands Meteorological Institute, the Australian Bureau of Meteorology, and the World Weather Attribution Consortium. The basic logic of the framework is this: we cannot run controlled experiments on the actual Earth. We cannot rewind time and observe what the 2026 climate would have done in the absence of the approximately 1–2 degrees Celsius of warming that has occurred since the late 19th century. We cannot construct a parallel Earth without anthropogenic forcing and observe what its weather is doing this week. But we can do something closely analogous in the model framework. We can run a climate model, typically an ensemble of state-of-the-art coupled atmosphere-ocean general circulation models, under two scenarios. The first scenario is the actual scenario, in which the model is forced with the observed historical concentrations of greenhouse gases, aerosols, and other anthropogenic forcings. The second scenario is the counterfactual scenario, in which the model is forced with pre-industrial concentrations of those same factors. We then compare the statistical distributions of extreme events between the two scenarios. The difference in the distributions tells us how much more frequent and how much more intense the extreme events have become as a result of the anthropogenic forcing. The numbers for extreme heat events in particular are striking. A 2019 paper in Nature Climate Change by Friederike Otto and colleagues at the University of Oxford and Imperial College London applied this framework to the 2018 European heat wave. The team estimated that the event was approximately 5 times more likely under the actual scenario than under the counterfactual pre-industrial scenario. A 2020 paper by the same group, examining the Russian heat wave of 2010, estimated that the event was approximately 3 times more likely under the actual scenario than under the counterfactual. A 2021 paper in Earth System Dynamics by Geert Jan van Oldenborg and colleagues at the Royal Netherlands Meteorological Institute, examining the Pacific Northwest heat dome of June 2021, came to a more striking conclusion. The team estimated that the event, in its observed magnitude, would have been virtually impossible, their term, without the underlying anthropogenic warming. The team estimated that the warming made the event approximately 150 times more likely. 150 times. Let me say that again so it registers. The 2021 Pacific Northwest heat dome was made approximately 150 times more likely by the warming that has occurred since the late 19th century. This is the kind of quantitative attribution that the framework now produces routinely. The preliminary application of the framework to this week's North American March heat event has not yet been completed. I cannot tell you today by how much the warming has made this event more likely. But the analog events I have just cited, the European heat wave of 2018, the Russian heat wave of 2010, the Pacific Northwest heat dome of 2021, all returned attribution multiples in the range of 3 to 150 times more likely under the actual scenario. The expectation, when the formal attribution is published for this week's event in the coming months, is that it will fall somewhere in that range. The combination of the extreme departure from climatology, +6.4 standard deviations, and the seasonal timing, March, before the population is acclimatized, suggests that the attribution multiple will be on the higher end of the range. The event may, in fact, be one of the events that future textbooks cite as a clear example of a heat extreme that was effectively impossible without the warming. This is the part that the climate skeptic framing cannot accommodate. The framing, in its standard form, says, heat waves have always occurred. The 1930s had heat waves. The 1950s had heat waves. This is normal weather. The framing is, in a narrow sense, correct. Heat waves have always occurred, but the framing misses the critical quantitative point. The frequency of extreme heat waves has increased. The magnitude of extreme heat waves has increased. The probability of an event of this week's magnitude, evaluated against the climatology of the 1930s or 1950s, is vanishingly small. The probability of an event of this week's magnitude, evaluated against the climatology of 2026, is meaningful. The dice are loaded. The fingerprint is in the data. The experiments, the model-based attribution experiments, confirm what the observational record suggests. This is not theory. This is the converged finding of multiple independent research groups, using multiple independent model frameworks, on multiple independent extreme events over the last 2 decades. The science is, on this point, settled. I want to come back to the surface, because the surface conditions that contributed to this week's heat dome, the dry soil column, the desiccated vegetation, the antecedent precipitation deficit, are themselves part of a longer story that the public conversation has not adequately tracked. Let me give you the current drought picture across the south-central United States, as of the most recent United States Drought Monitor release. The United States Drought Monitor, maintained jointly by NOAA, the United States Department of Agriculture, and the National Drought Mitigation Center at the University of Nebraska-Lincoln, classifies drought intensity on a 5-tier scale from D0, abnormally dry, through D4, exceptional drought. The most recent release, dated March 6, 2026, shows the following classifications across the south-central United States. Southern Texas, D2 to D3, severe to extreme drought. Central and western Texas, D1 to D2, moderate to severe drought. Oklahoma Panhandle, D2 to D3, severe to extreme drought. Southwestern Kansas, D1 to D2, moderate to severe drought. Eastern New Mexico, D2 to D4, severe to exceptional drought. Southeastern Colorado, D1 to D2, moderate to severe drought. The total area in some level of drought classification across the south-central United States, as of March 6, is approximately 280,000 square miles. That is an area larger than the state of Texas itself. The accumulated precipitation deficit, calculated against the 1991 to 2020 climatological mean, for the 12-month period ending February 28, 2026, runs in the range of 4 to 10 inches deficit across most of the affected area, with localized deficits in West Texas and eastern New Mexico exceeding 12 inches. The vegetation across the affected area, going into the March heat event, was in a state of stress that had been building for over a year. The native rangeland grasses, which depend on cool season precipitation, had not received the moisture they needed during the December through February window. The winter wheat crop, planted in the fall of 2025 across the Texas, Oklahoma, and Kansas wheat belt, was, by the most recent USDA crop progress report, rated 35% poor to very poor, a rating that, historically, corresponds to crop yield losses of 30 to 50% at harvest. The early spring forbs and wildflowers, normally beginning their emergence in early March across South Texas, were, in many areas, simply not emerging at all due to the soil moisture deficit. Into this drought-stressed landscape, the March heat dome arrived. The amplification mechanism is straightforward. Dry soil, as I described in Part 2, heats more efficiently than moist soil because there is no latent heat draw from evaporation. But the amplification goes beyond the direct soil heating. Drought-stressed vegetation transpires less water vapor than well-watered vegetation, which means the regional latent heat flux from the land surface is reduced, which means more of the incoming solar radiation goes into sensible heat, into warming the air directly, rather than into latent heat. The boundary layer warms faster, the deep mixed layer extends higher, the afternoon temperatures climb further. A 2020 paper in Geophysical Research Letters by Renaud Falga and colleagues at the European Center for Medium Range Weather Forecasts quantified this effect. The team examined the role of antecedent soil moisture in the magnitude of heat extremes across Europe and North America. They found that, in regions experiencing significant precipitation deficit going into a heat event, the peak afternoon temperatures during the event run approximately 1.5 to 3 degrees Celsius higher than they would have run with average antecedent soil moisture. That is a 2.7 to 5.4 degrees Fahrenheit amplification, attributable to the antecedent dryness alone. For this week's event, the antecedent dryness amplification is likely in the upper portion of that range. The 105 in McAllen, in other words, is not just a heat dome temperature. It is a heat dome temperature amplified by drought. Without the drought, the McAllen high might have been 101 or 102. With the drought, the high was 105. This is the kind of compound mechanism that makes events like this week so dangerous. The heat dome and the drought are not separate. They are coupled. The drought made the heat dome worse. And the heat dome, through the increased evapotranspiration demand it imposes on already stressed vegetation, through the surface drying it produces, through the negative feedback on regional precipitation that subsidence inversions impose, is, in turn, making the drought worse. The bathtub is filling, the faucet is open, the drain is closing, and here is the part the public conversation almost never adequately captures. The drought is itself, in part, a fingerprint of the warming signal. The south-central United States, particularly Texas, has experienced a statistically significant trend toward increased precipitation variability and increased peak warm season temperatures over the last several decades. The 2024 paper in Nature Communications by John Nielsen Gammon and colleagues at Texas A&M University documented that the frequency of multi-year drought episodes in Texas has approximately doubled since the mid-20th century, and that the rate of drought intensification, the speed at which a region transitions from D0 to D3 conditions, has approximately tripled. The team termed the latter phenomenon flash drought. Flash drought is a relatively new operational concept in climate science. It refers to drought episodes that develop within weeks rather than years, driven primarily by anomalously high temperatures and anomalously high evapotranspiration demand rather than by long-term precipitation deficit. Flash drought is, by every metric the operational community can apply, increasing in frequency, particularly across the south-central United States. The drought going into this week's heat dome was not, primarily, a flash drought. It was a multi-month accumulated deficit. But the flash drought mechanism is now operating on top of that deficit, accelerating the soil moisture decline, intensifying the vegetation stress, and setting up conditions for further heat amplification in the weeks ahead. The compound is compounding, the system is feeding itself, the window is closing. I want to take you briefly into the longer-range forecast, because the question that follows naturally from this week's event is, what comes next? The standard caveats apply. Long-range forecasts, beyond approximately 10 days, are dominated by uncertainty. The skill of model forecasts decays with lead time. Statements about what will happen in May, made in March, are statements about probabilities and tendencies, not statements about specific outcomes. Any individual May 2026 day is not predictable from March 2026 information, but the climate forecasting system can give us probabilistic information about the broader pattern. And that probabilistic information, as it currently stands for May 2026 across the south-central United States, is concerning. The Climate Prediction Center's 3-month outlook, issued February 20, 2026 and updated weekly, places the south-central United States in the above normal temperature category for the March through May period, with probabilities exceeding 60% in the highest confidence areas. The corresponding precipitation outlook places the same area in the below normal precipitation category, with probabilities exceeding 50%. Above normal temperature, below normal precipitation, for the 3-month period that includes the rest of March, all of April, and all of May. The current event, the March heat dome, is consistent with that outlook. The outlook does not necessarily mean that the same magnitude of heat will recur in April or May. But the outlook does suggest that the underlying drivers, the sea surface temperature pattern, the soil moisture anomalies, the broader atmospheric circulation, are favorable for continued warm and dry conditions across the region for the next several months. If the pattern continues into May, the implications are not abstract. May is the peak severe weather month for the central United States. May is the month in which the corn crop is planted across the Midwest. May is the month in which the cattle on the southern plains are most vulnerable to heat stress. May is the month in which the water supply systems across the southern plains depend most heavily on snowmelt from the Rocky Mountain headwaters and the snowpack in the southern Rockies. As of the most recent NRCS snow survey, is running at approximately 65% of the 1991 to 2020 median. A continued warm and dry pattern through May would extend the agricultural stress that the winter drought has already initiated. The winter wheat harvest in the southern plains, scheduled for late May through June, would face the prospect of significantly reduced yields. The corn planting across the Midwest, dependent on adequate soil moisture at the time of planting, would face challenges in the corridor where the heat dome's influence has dried the surface most efficiently. The cattle industry across Texas, Oklahoma, and Kansas, already stressed by 18 months of accumulated drought, would face another round of forced herd reductions. The economic exposure is not abstract. The agricultural economy of the south-central United States is on the order of $200 billion annually in farm gate value. A 10% reduction in agricultural output across the region, sustained over a single season, is a $20 billion impact. Compound it with the construction industry impact, the energy industry impact, the water utility impact, and the public health impact, and the cascading economic consequences of a severe warm season drought across the south-central United States exceed $50 billion in a moderate scenario. Then there is the cascading effect on the broader severe, weather forecast for the central United States during the May into June period. In the previous video on this channel, I walked you through in detail the mechanism by which drought to the west of the Central Plains contributes to the sharpening of the dry line that initiates severe weather outbreaks across the eastern plains. That mechanism is loaded right now. The drought is in place. The heat dome has further amplified the surface drying. If the pattern continues into May and June, the severe weather environment across the eastern plains, in conjunction with deep Gulf moisture transport, has the potential to be exceptionally favorable for the most intense severe weather outbreaks. The chain is connected. The drought feeds the heat dome feeds the drought feeds the dry line feeds the severe weather. The severe weather feeds the recovery gap feeds the cascading economic impact. The cascading economic impact feeds the political and social stress that comes with sustained regional crisis. This is the part of the heat dome story that the temperature numbers alone do not capture. The temperature numbers are the present moment. The chain is the future. And the chain this week is being loaded. I have to spend some time on the misinformation cycle because we are 72 hours into the event and the cycle is already in full swing. By Tuesday afternoon, the social media environment around the heat dome had already begun to fragment into 3 categories of misleading framing. I want to walk through each one, name the mechanism by which the framing fails to engage with the actual data, and pivot to what the real explanation actually is, because the gap between the conspiracy framing and the real explanation is, again, part of what this channel exists to close. The first category is the weather manipulation claim. By Tuesday evening, posts on X, TikTok, and Telegram were circulating claims that the heat dome was the result of HAARP transmissions, of cloud seeding gone wrong, of geoengineering experiments, of various unspecified, doing something to the atmosphere to produce the heat. I addressed this category in detail in the previous video. The same energy budget argument applies here. The total energy required to warm the lower atmosphere across the south-central United States by 8 to 10 degrees Celsius for several days is on the order of 10 to the 21st power joules. That is approximately 250 trillion megajoules. There is no human technology, not HAARP, not cloud seeding, not any extant geoengineering platform that can deliver energy on that scale to the atmosphere. The total annual primary energy consumption of the entire United States is approximately 10 to the 20th power joules. The energy required to produce the heat dome is approximately 10 times the annual energy consumption of the United States, concentrated over a 96-hour window over a continental-scale area. There is no mechanism by which any extant technology could deliver that energy. The mechanism is solar energy, trapped beneath a subsidence inversion, accumulated day over day. That is the mechanism. That is the only mechanism. The energy budget does not work. Full stop. The second category is the "this happens every year" claim. By Tuesday evening, posts were circulating from accounts framing the heat dome as a normal seasonal occurrence, pointing to other March heat events from previous years, framing the current event as media hype around something that has happened repeatedly. There is a kernel of truth in this framing. March heat events do occur. The previous March records from 1971, the more recent March records from 2008, all represent genuine heat events that occurred in the past. The framing is not wrong to point this out, but the framing fundamentally misses the quantitative magnitude of this week's event. The 1971 March heat event, which set previous records across South Texas, had a McAllen high of 102 degrees Fahrenheit. The 2026 event has a McAllen high of 105 degrees Fahrenheit. That is a 3-degree margin in a record that had stood for 55 years. The 2008 March heat event had Wichita and Topeka highs of 88 and 86 degrees. The 2026 event has tied or exceeded those values across a much larger geographic area and with a more spatially coherent ridge structure. The 1907 March maximum in Houston was 89 degrees. The 2026 March maximum in Houston was 92 degrees. The "this happens every year" framing requires you to ignore the magnitude of the record breaking and the spatial coherence of the event. Both are unprecedented in the modern record. The previous events were point anomalies, a single station, a single day, a margin of 1 or 2 degrees. This week's event is a continent-scale anomaly. Hundreds of stations, multiple days, margins of 1 to 5 degrees, with a +6.4 sigma 500 millibar height field driving it. These are not the same kind of event. The 1971 event was a one-station-at-a-time outlier. The 2026 event is a regional regime shift. The third category is the data is being manipulated claim. By Wednesday morning, posts were beginning to circulate alleging that the temperature data being reported by the National Weather Service had been adjusted upward to produce alarming numbers, that the observing equipment had been moved to artificially warmer locations, that historical records had been retroactively cooled to make modern records appear more extreme. This category requires a different kind of response. The temperature data collected by the National Weather Service is, in a meaningful operational sense, the most carefully maintained and most thoroughly scrutinized environmental data on Earth. The automated surface observing system sites are subject to documented siting standards. The historical records are subject to documented quality control procedures. The adjustments to historical records, when adjustments are applied, are documented in peer-reviewed papers, are applied transparently, are applied to correct known biases such as the time of observation bias and the station move bias, and are, on net, smaller than the changes being claimed by the conspiracy framing. The temperature trends visible in the U.S. observational record have been replicated independently by groups using satellite data, by groups using ocean heat content data, by groups using glacier mass balance data, by groups using boreal treeline shift data, by groups using species range shift data, by groups using growing season length data. Multiple independent observational systems, none of which depend on the NWS surface station record, are converging on the same conclusion. The Earth is warming. The continent is warming. The records being broken this week are real. The conspiracy framing requires you to believe that all of these independent observational systems have been simultaneously manipulated by the same actors. Across multiple national meteorological agencies, across multiple academic research institutions, across multiple satellite programs operated by multiple nations, across multiple decades. The coordination problem alone makes the conspiracy untenable. The data is real. The records are real. The signal is in the observations. Sit with that. The real explanation, again, is more alarming than the conspiracy. The conspiracy framing, if it were true, would mean the warming is illusory and the records are manufactured. There would be no real signal to worry about. The framing offers comfort. The real explanation is that the warming is real, the records are real, and the trend is continuing. There is no manufactured signal to debunk. The signal is in the data, in the observations, in the satellite measurements, in the ocean heat content, in the glacier retreat, in the species range shifts, in the growing season length, in the wet bulb temperature exceedances, in the wildfire frequency, in the marine heat wave duration, in every metric the planetary observing system can produce. The comfort offered by the conspiracy framing is false. The discomfort offered by the real explanation is earned. Earned in the sense that the discomfort comes from honestly engaging with what the data tells us. And the data tells us this week that the south-central United States in March 2026 has been visited by a heat dome of a magnitude that the historical record has not previously produced. The framing matters. The framing determines whether the public conversation engages with the actual signal or with the imagined one. The cosmic forecast is every week in the business of pushing the framing toward the data, toward the observations, toward the mechanism, toward the consequences. That is the work. I want to walk you through, specifically, the categories of infrastructure across the south-central United States that are being tested by this week's event. Because the infrastructure stress is one of the most underappreciated consequences of extreme heat in unusual seasonal timing. Electrical grid. The electrical grid across the south-central United States is operated primarily by the Electric Reliability Council of Texas in Texas, by the Southwest Power Pool across Oklahoma, Kansas, and parts of New Mexico, and by the Mid-Continent Independent System operator across the Midwest. Each of these grid operators maintains seasonal capacity planning based on historical peak demand patterns. Their planning assumes that peak demand in March is dominated by morning heating loads, not afternoon cooling loads. This week, that assumption is wrong. The afternoon cooling load across South and Central Texas on Tuesday, March 11, exceeded the typical March afternoon load by approximately 35 to 50%. ERCOT issued an operational notice on Tuesday afternoon, flagging the elevated load and confirming that all available generation was online. The grid held, but the operational margin was narrower than the grid operator had planned for. If a major generation unit had tripped offline during the peak load window, ERCOT would have faced a potential supply-demand mismatch. The challenge is not the absolute load. The challenge is the seasonal timing. March is when grid operators schedule maintenance outages on generation units, expecting low demand. A heat dome in March arrives when a meaningful fraction of generation capacity is offline for scheduled maintenance, which compresses the operational margin further. If this week's heat dome had occurred 2 or 3 weeks later, with more units online from the backside of maintenance season, the grid stress would have been smaller. The timing this week is approximately the worst possible timing for an extreme heat event from the grid operator's perspective. Water infrastructure. The water utilities across the south-central United States operate on demand assumptions that include strong seasonality. Outdoor water use, irrigation, lawn watering, agricultural application typically begins to ramp up in mid-April across South Texas and in mid-May across the Central Plains. This week, with afternoon temperatures in the 90s and 100s across an enormous area, outdoor water use has begun approximately 5 to 6 weeks earlier than the utilities had planned for. The result is that water systems are drawing harder on storage and supply than they typically would in March. In regions where storage reservoirs are already drawn down from the multi-year drought, and that is currently most of the south-central United States, the additional March demand is accelerating the storage decline. Several municipal utilities across central Texas have, as of Tuesday, initiated voluntary water conservation measures earlier than they typically would. Several more are likely to follow in the coming days. Agriculture and livestock. The agricultural sector across the south-central United States is, in early March, in a transitional phase. Winter crops, primarily winter wheat, are in the late vegetative or early reproductive stages. Spring crops, primarily corn and cotton, are in the planting phase or about to enter it. The livestock sector is in the calving and lambing phase, with newborn animals particularly vulnerable to thermal stress. This week's heat dome has hit at the worst time for each of these subsectors. The winter wheat crop, already stressed by drought, is experiencing forced premature reproductive transition under the heat, a phenomenon called heat blast in wheat agronomy, which reduces grain fill and lowers yield. The corn and cotton planting is being accelerated in some regions to take advantage of the warm soil. But the lack of soil moisture is creating planting decisions that may not pay off if the warm and dry pattern continues. The livestock sector is reporting elevated newborn mortality in operations across South Texas, particularly in operations that lack the cooling infrastructure that summer month operations would have deployed. Public health. The public health system across the south-central United States is, in March, calibrated for a different problem set than the one that is suddenly emerging. The seasonal flu season is still winding down. The pollen season is still ramping up. The wildfire smoke season has not yet begun. The cooling centers, the public facilities that municipalities open during summer heat events to provide air-conditioned refuge to vulnerable populations, are not staffed, not stocked, and in many cases, not even publicly identified for the March timeframe. As of Tuesday evening, multiple counties across South Texas had begun the process of opening cooling centers earlier than they had been scheduled to. The staffing was being assembled hour by hour. The public messaging, the announcements of cooling center locations and hours, was being distributed through social media and local broadcast partners. The vulnerable populations who would most benefit from cooling center access, the elderly without air conditioning, the unhoused, the workers without indoor refuge options, were being identified and contacted by emergency management staff who had not, until this week, expected to be running these protocols in March. Each of these infrastructure systems was, in March 2026, designed and operated against the assumption of a March that no longer exists. Each of them is being asked, this week, to perform functions that they typically perform in June or July. Each of them is performing with significant operational stress, but with success that is dependent on the heat dome breaking before the systems run out of operational margin. The systems were not designed for a calendar that has become unreliable. The systems are being reformatted, this week in real time, to handle a calendar that no one explicitly chose, but that the atmosphere is increasingly imposing. This is the second-order cost of extreme weather in the wrong season. The first-order cost is the direct human and economic impact of the heat itself. The second-order cost is the infrastructure stress that comes from the systems being asked to operate outside their design envelope. We are paying both costs this week. We will pay more of them, more often in the years ahead, as the calendar continues to slide. I want to take a moment with the social dimension of extreme heat, because the public conversation around heat waves tends to frame the event as a universal experience, when in fact the experience of heat is among the most stratified experiences in modern society. Consider two households, both located in the Rio Grande Valley of South Texas. Both households experienced the same outdoor temperature this week, 105 degrees on Tuesday afternoon, 102 on Wednesday afternoon, 99 on Thursday afternoon. The outdoor temperatures are identical. The indoor temperatures are not. Household A is a single-family home built in 2018 with R30 ceiling insulation, double-pane low-emissivity windows, a 16-SEER central air conditioning system that was installed at construction, and a backup window unit in the master bedroom. The household on Tuesday afternoon. maintains an indoor temperature of 76 degrees Fahrenheit at a monthly electricity cost that is elevated above the March baseline, but is manageable within the household budget. Household B is a 1960s vintage frame house with minimal ceiling insulation, single-pane aluminum frame windows, no central air conditioning, and two failing window units that the household has not been able to afford to replace. The household, on Tuesday afternoon, maintains an indoor temperature of 89 degrees Fahrenheit in the room with the better functioning window unit, and 95 degrees in the rest of the house. The window unit electricity consumption, projected over the duration of the heat dome, will produce a March electricity bill that exceeds the household's monthly food budget. Both households are experiencing the same heat dome. They are not experiencing the same heat. This is the operational reality of extreme heat in the United States in 2026. The capacity to escape extreme heat is, in a meaningful sense, a function of household wealth. Insulation costs money, windows cost money, air conditioning costs money, electricity costs money. Each of these inputs is a stair and a staircase that separates the population that can be comfortable in extreme heat from the population that cannot. The mortality data on extreme heat events reflects this stratification with clarity that should be uncomfortable. The 2003 European heat wave, which I have referenced repeatedly in this video, produced an estimated 70,000 excess deaths across Western Europe. The deaths were not evenly distributed across the affected population. They were concentrated heavily in the elderly, in the urban poor, in the residents of buildings without modern cooling, in the workers in outdoor occupations, in the institutionalized populations of nursing homes and prisons. The mortality rate in the French nursing home population during the August 2003 peak was multiple times the baseline mortality rate. The 2021 Pacific Northwest heat dome, which produced an estimated 600 excess deaths across the region, showed similar stratification. The deaths were concentrated in homes without air conditioning, and the Pacific Northwest has a higher percentage of homes without air conditioning than any other major region in the United States, because the historical climatology has not required cooling infrastructure to be standard. The transition to a warmer climate found the region's housing stock ill-prepared, and the people in the homes most ill-prepared were the people who died. The same stratification is, this week, playing out across the south-central United States. The workers who are most exposed to the heat are the agricultural workers in the fields, the construction workers on outdoor sites, the warehouse workers in buildings without adequate climate control, the delivery drivers in vehicles without functioning air conditioning, the food service workers in restaurants without sufficient ventilation. Each of these occupations has a workforce that skews lower income and is disproportionately composed of recent immigrants and seasonal workers. The Texas Department of State Health Services maintains a heat-related illness reporting system, and the data from previous years shows clearly that the population presenting with severe heat illness is, demographically, the population that has the least capacity to escape the heat. Outdoor laborers, low-income elderly, low-income parents managing children in homes without adequate cooling, the unhoused population. This week's heat dome, occurring in March, is adding several specific complications to the stratification picture. The seasonal cooling assistance programs operated by various states and local agencies, programs designed to help low-income households pay summer cooling bills, typically begin their assistance periods in May or June. They are not yet in operation in March. The households who would most benefit from cooling assistance are, this week, paying the elevated electricity bills out of pocket, in many cases by deferring other essential expenses. The seasonal employment protections for outdoor workers, heat illness prevention regulations, mandatory water and rest breaks, employer cooling provisions are, in some jurisdictions, not yet in force for the March timeframe. Where they are in force, they are not yet being enforced with the same vigor that the summer months bring. The workers who are most vulnerable to occupational heat illness this week are working under regulatory frameworks that are calibrated for a different month. The seasonal awareness around heat illness, the public health messaging, the school nurse training, the emergency department screening protocols is, in March, at a low point. Schools that in July would have a heat illness protocol active for outdoor athletics, in March may have only the standard cold weather protocols active. Coaches who, in July, would know to look for the signs of exertional heat illness, in March may be less attuned. Parents who, in July, would not let their kids do an extended outdoor practice without hydration, in March may not consider it. The protections are absent or attenuated. The exposure is the same as it would be in summer. The mortality risk, particularly for the vulnerable subpopulations, is, in proportional terms, higher this week than it would be in an equivalent summer heat event. This is the operational reality of a calendar that has become unreliable. The protections that the society has built up to handle extreme heat are calibrated to the calendar. When the calendar slides, the protections slide out from under the people who need them most. I want to take a moment with a specific concept, because the science writing around extreme heat tends to default to comparison with the historical record. And the historical record has a fundamental limitation that the public conversation does not adequately reckon with. The modern, instrumented temperature record for the United States goes back, in continuous form at significant station coverage, to approximately 1880. That is roughly 146 years of record. For some regions of the country, the continuous record is shorter. For the western interior, much of the high-quality record begins after 1900, and for some interior stations, after 1930. 146 years sounds like a long record. By the standards of human history, it is. By the standards of human direct experience, it spans approximately 7 human generations. But by the standards of geological time, 146 years is nothing. The atmospheric and oceanic system that produces weather operates on timescales ranging from minutes, for individual thunderstorms, to thousands of years, for the deep ocean circulation. The full range of natural variability that the system can produce is not captured in 146 years of record. The record we have access to is, in statistical terms, a tiny slice of the underlying distribution. What this means, practically, is that when we describe an event as unprecedented in the modern record, we are making a statement about a 146-year window. We are not making a statement about what the system can, in principle, produce. The system may be capable of producing events that exceed everything in the modern record by significant margins, events that simply did not occur in our 146-year window of observation, by chance. The +64 sigma 500 millibar height anomaly that the climate diagnosticians are reporting this week is a statement evaluated against the modern record. Against the actual distribution of possible atmospheric states, the event may be less extreme than the modern record statistic suggests. The atmosphere has, in past geological epochs, produced configurations far more extreme than anything in the modern record. The Holocene climatic optimum, between 8,000 and 5,000 years ago, produced sustained summer temperatures across the mid-latitudes that exceeded modern summer temperatures by several degrees Celsius. The Eocene thermal maximum, 56 million years ago, produced global mean temperatures approximately 6 degrees Celsius above modern values. The atmosphere can do things we have never seen. The question, for our purposes, is whether the events we are now witnessing are the leading edge of the atmosphere doing things it has not done in millennia. The paleoclimate record, reconstructed from tree rings, ice cores, lake sediments, and corals, can give us some context. The most relevant paleoclimate reconstruction for our purposes is the multi-proxy reconstruction of the past 2,000 years of Northern Hemisphere temperature variability. Originally published in a series of papers by McAllen and colleagues beginning in 1998 and substantially refined and extended by multiple research groups since then. The most recent, peer-reviewed consensus reconstruction, published in 2019 by the PAGES-2K Consortium in Nature Geoscience, shows that the Northern Hemisphere mean temperature for the most recent decade, 2010 to 2019, was the warmest decade in the 2,000-year reconstruction by a margin that significantly exceeds the proxy. Uncertainty. The warmest decade in 2,000 years, the decade that ended 6 years ago. The 2020s, as of the current data, are continuing the trend. The 2020 to 2025 average is, in the early returns, running ahead of the 2010 to 2019 average by approximately 0.2 degrees Celsius globally and approximately 0.3 degrees Celsius across the Northern Hemisphere. We are not, this decade, just breaking modern instrumental records. We are, by every paleoclimate reconstruction that the science community can produce, in the upper tail of the distribution for the past 2,000 years. The atmospheric column over the south-central United States this week is, in temperature terms, warmer than it has been for the date in any reconstructed year going back to the early Holocene. By the best estimates the proxies can support. This is the part that I want you to sit with. Nobody alive has ever seen before what the atmosphere is doing right now over North America. Not because the event is unprecedented in the modern record. That is true, but it is not the deepest layer of the story. The deepest layer is that the modern record is itself nested inside a longer paleoclimate record, and against that longer record, the present moment is, increasingly, in territory that has no analog at any human or near-human timescale. The thing we are now calling March in Texas is not a march that any human population has previously inhabited. The signal is in the data. The data goes back, by proxy, 2,000 years. The signal points one direction. The window is closing. The math has changed. The dice are loaded. These are not rhetorical flourishes. These are descriptions of what the paleoclimate science actually says. This is the cosmic forecast in the business of translating, with precision, what the science actually says. Not what the alarmist version says, not what the dismissive version says, what the data, taken on its own terms, actually says. The data says, this week's event is not primarily weather. The data says, this week's event is climate. I want to walk through one specific cascading impact that is now beginning to develop downstream of the heat dome, because this impact is among the most consequential and least anticipated, and it is going to dominate parts of the news cycle in the coming days. The dry, hot, well-mixed boundary layer that the heat dome is producing across the south-central United States is generating, as a downstream consequence, the most active dust storm regime that the region has experienced in March in the modern record. As of Tuesday afternoon, multiple dust storm events had been documented across West Texas, eastern New Mexico, the Oklahoma Panhandle, and southwestern Kansas. The visibility on portions of Interstate 40 and Interstate 27 had dropped to less than a quarter mile during the worst of the dust events. The mechanism is straightforward. The drought has dried the soil. The vegetation cover is reduced. The boundary layer mixing, driven by the heat dome, has reached deep into the lower atmosphere. The horizontal pressure gradient embedded in the synoptic pattern is producing surface winds of 35 to 50 knots, gusting to 65 knots across the affected region. Dry soil, sparse vegetation, deep mixing, strong winds. That is the dust storm recipe. The dust storms are not just a visibility hazard, they are a public health hazard. The fine particulate matter, PM2.5, concentrations in the affected areas during the peak of the dust events on Tuesday afternoon exceeded the EPA 24-hour standard by factors of 10 to 20. Air quality indices across portions of West Texas and eastern New Mexico reached the hazardous category, the highest classification on the AQI scale. The hazardous category in the EPA's framework corresponds to conditions in which everyone should remain indoors, and in which active children and adults and people with respiratory disease should avoid all outdoor exertion. This is in March. This is being driven by the heat dome. The dust storms are also a transportation hazard. The Texas Department of Transportation, working with the Texas Department of Public Safety, has implemented temporary closures on portions of Interstate 27, Interstate 40, and several state highways during the worst of the dust events. The closures are not minor. They reroute through traffic by hundreds of miles in some cases. The economic cost in fuel, in lost time, in supply chain disruption to the regions that depend on those highways is significant. And the dust storms are, in their epidemiological consequences, going to be a longer-tail public health story than the heat dome itself. The literature on dust storm exposure and respiratory health is, by now, well established. A 2019 paper in Environmental Health Perspectives by Daniel Tong and colleagues at NOAA's Air Resources Laboratory documented that dust storm events across the United States are associated with statistically significant increases in emergency department visits for asthma, COPD, and acute respiratory infections in the weeks following the events. The 2024 update to that analysis, examining more recent dust events, has shown that the magnitude of the respiratory health impact scales with the duration and intensity of the dust exposure, and that the population most affected is, again, the population with the least capacity to escape, the workers in outdoor occupations, the unhoused, the residents of homes without functioning HVAC filtration. This week's dust events are particularly intense by the operational record. The 2024 paper in Geophysical Research Letters by Daniel Tong's group documented a quadrupling of dust storm frequency across the south-central United States since the 1990s, with the most extreme events showing the steepest increase. This week's events are the latest data point in that trend. The dust storms are part of the heat dome. The heat dome is part of the drought. The drought is part of the warming signal. The chain is continuous. The respiratory illness data, when it filters through the public health reporting system in the coming weeks, will reflect this week's events. The mortality data, particularly in the elderly and the chronically ill, will reflect it. The economic data, when it reflects the transportation closures and the supply chain disruptions, will reflect it. This is what the unwound calendar looks like. This is what happens when the climate envelope shifts under infrastructure, regulation, and public health systems calibrated for the old envelope. The window is closing. The chain is loading. I want to take you, with specificity, into the agricultural sector across the south-central United States. Because the agricultural impacts of this week's event are going to play out over the next 12 to 18 months, and the impacts will be measured in billions of dollars, in shifted commodity prices, and in the long-term restructuring of the regional agricultural economy. Let me start with winter wheat. The winter wheat crop across the southern plains, Texas, Oklahoma, Kansas, and Colorado was planted in the fall of 2025 across approximately 25 million acres. The crop, by early March, is typically in the late vegetative stage, beginning the transition to reproductive growth as the photoperiod and temperature signals trigger jointing and head emergence. The crop is, at this stage of development, particularly sensitive to extreme temperatures, because the meristematic tissue that will become the wheat head is being actively differentiated. And high temperatures during this differentiation process produce permanent yield loss through reduced floret formation. This week's heat dome arrived during the peak vulnerability window for winter. Wheat across the southern plains. The Texas A&M Agri-Life Extension Service, in coordination with the National Weather Service, issued a guidance bulletin on Tuesday flagging the elevated risk of heat-induced yield loss in the affected crop. The preliminary assessment, pending the recovery period and the field surveys that will follow, is that yield losses across the affected wheat belt could be in the range of 15 to 30% for crops that were already stressed by the multi-month drought. A 15 to 30% yield loss across 25 million acres of winter wheat is, in financial terms, a $1.5 to $3 billion impact at current wheat prices. That is the direct financial impact. The indirect impact, through the cattle sector that depends on wheat pasture for late winter and early spring grazing, is additional. Let me transition to corn. The corn crop across the central United States, including the south-central states currently under the heat dome, is at the planting stage. The decision of when to plant is made by individual farmers based on soil temperature, soil moisture, and the longer-range weather forecast. Soil temperatures across the south-central states this week have surged above the 50-degree threshold, that is the minimum for reliable corn germination. The temptation for farmers is to plant early to take advantage of the warm soil. The temptation is dangerous. Corn planted into warm, dry soil this week will germinate quickly, but the seedlings will be vulnerable to multiple subsequent risks. The first is the risk of late-season frost. The climatological probability of a damaging frost in the south-central states extends into mid-April in some regions. And the historical record contains examples of frost events that have damaged corn that was planted too early. The second is the risk of continued drought, which would stress the young corn during its critical early establishment phase. The third is the risk of a transition to wetter conditions that would, ironically, leave the early planted corn vulnerable to seedling disease in cold, wet soil after the warm and dry pattern breaks. The agronomic decision is genuinely difficult. The farmers across the affected region are making it, this week, with imperfect information and elevated risk on all sides. Let me transition to cattle. The cattle inventory across the south-central United States, the breeding stock that produces the calves that, 18 months later, become the beef in the American food supply, has been declining for multiple years. The accumulated drought has reduced grazing capacity. The forage costs have risen. The producers have responded by reducing herd size to match the forage availability. The U.S. cattle inventory, as of the most recent USDA estimate, is at the lowest level in approximately 75 years. This week's heat dome, hitting in March, is adding multiple new stresses to a sector already under sustained pressure. The grazing pastures across the south-central states are not at full productivity for the season. The grasses that should be greening up are, in many areas, still dormant or sparse. The supplemental feed that producers have been providing through the winter is being consumed at higher rates than projected. Because the cattle are using more energy on thermoregulation in the elevated temperatures, the newborn calves, and March's calving season across much of the region, are vulnerable to heat stress that they would not normally encounter at this stage of life. The cumulative effect on the cattle sector is to accelerate the herd liquidation that has already been underway. Producers who were on the margin of profitability, operating at break-even or small losses, with the hope that the drought would end and forage conditions would improve, are this week being pushed across the line into forced liquidation. The auction barns across South Texas reported on Tuesday elevated volumes of cattle being moved to market animals that, under more favorable conditions, would have been held for breeding or finishing. The forced liquidation has implications that extend beyond the affected producers. The reduction in the breeding herd means a smaller calf crop in 2027, which means a smaller beef supply in 2028 and 2029. The price effect in the wholesale and retail beef market will be a continued upward trajectory in beef prices through the second half of the decade. The consumers, every American who eats beef, will pay the cost of this week's heat dome in the price they pay at the grocery store for years to come. This is what a calendar that has become unreliable does to an agricultural system. The system is, at every level, optimized for the calendar that was. The crop selection is optimized. The planting dates are optimized. The grazing rotation is optimized. The breeding schedule is optimized. The infrastructure investment is optimized. When the calendar slides, every piece of the optimization slides with it. The crops are exposed to risks they were not selected for. The planting dates produce outcomes they were not intended to produce. The grazing rotation collapses against forage that has not arrived. The breeding schedule produces newborns that face conditions they were not adapted to. The system can adapt. The system is, in fact, in the process of adapting. The agricultural extension services, the seed companies, the cattle breed associations, the irrigation district managers, the federal crop insurance program, all are, in their various ways, working to update the optimizations for the calendar that is, rather than the calendar that was. But the adaptation is slow. The depreciation cycles of major agricultural infrastructure are measured in decades. The breeding programs that produce livestock genetics are measured in generations. The crop variety development pipelines are measured in 5 to 10-year intervals. The institutional knowledge that determines what farmers know how to do is measured in generations. The calendar is sliding faster than the system can adapt. The gap is widening. The window is closing. I want to take a moment with the policy environment, because the policy environment determines what the United States is able to do in response to events like this week's heat dome. And the policy environment in March 2026 is, by every metric I can find, not configured to respond at the scale that the events are now producing. Let me give you several specific examples. The Federal Disaster Declaration Framework. The Stafford Act, which governs federal disaster response and recovery, was originally passed in 1988. The act has been amended multiple times since, but the core framework, the process by which a governor requests federal assistance, the criteria by which FEMA evaluates the request, the categories of assistance available, has remained largely unchanged for nearly 4 decades. The framework was designed for a disaster frequency, scale, and type that was characteristic of the 1980s. The frequency of qualifying events has, as documented in my previous video, increased by approximately 7-fold since the 1980s. The framework is, as a result, processing approximately 7 times the workload it was designed for, with budget and staffing that have not increased proportionally. The result is that disaster declarations are delayed, recovery funding flows more slowly, individual assistance reaches affected households months after the event. The mismatch between the system's capacity and the workload is, by every measure the Government Accountability Office has produced, growing. The Federal Flood Insurance Program. The National Flood Insurance Program, administered by FEMA, is the primary flood insurance vehicle for residential and small commercial properties in the United States. The program operates on a premium structure that is, by the program's own admission, undercharging for the risk being insured. The program's accumulated debt to the Treasury, as of the most recent reporting, exceeds $20 billion. The program is, in practical operational terms, insolvent. The risk being insured is increasing, both because the climate is shifting flood probabilities and because the development of flood-prone areas continues. The premiums are constrained by political and regulatory considerations that have made full actuarial pricing impossible. The program continues to operate because Congress continues to appropriate funds to cover its losses. The system is structurally unsustainable, and the structural unsustainability is accelerating. The Department of Agriculture's Crop Insurance Program. The Federal Crop Insurance Program, administered by the Risk Management Agency of the USDA, is the primary risk management tool for U.S. agriculture. The program covers approximately 380 million acres of farmland and pays out, on average, approximately $10 to $15 billion per year in crop insurance indemnities. The indemnity payments have, in recent drought and heat years, reached as high as $19 billion. The program is, in its current configuration, subsidized at approximately 60%, meaning that taxpayers fund 60% of the premium cost, with farmers paying the remaining 40%. The indemnity payments from this week's heat dome will, when the agronomic impacts are quantified, contribute to the 2026 indemnity total. The 2026 total, projected from current conditions across the multi-region drought and heat picture, is likely to exceed $15 billion. The federal subsidy that covers 60% of the premium structure is therefore committing the federal budget to billions of dollars in payouts that, in a stationary climate, would not have been necessary at this scale. The Department of Energy's Grid Resilience and Reliability Investments. The federal investment in electrical grid resilience and reliability, principally through the bipartisan infrastructure law passed in 2021, allocated approximately $65 billion to grid modernization over a 5-year period. The investment is, by any reasonable assessment of the underlying need, inadequate. The total estimated cost of bringing the United States electrical grid up to the resilience standards that the projected climate scenarios will require is, by various estimates, in the range of $500 billion to $1 trillion over the next 2 decades. We are investing, federally, at 1/10 the rate that the resilience need is accumulating. The Environmental Protection Agency's air quality regulations. The EPA's primary air quality standards, the National Ambient Air Quality Standards, were established by the Clean Air Act of 1970 and have been periodically updated since. The standards address several categories of pollutants, including ozone, particulate matter, sulfur dioxide, and nitrogen dioxide. The standards do not, in their current form, adequately address the rising threat from wildfire smoke or from dust storms, which are now contributing to air quality exceedances in many regions of the country. This week's dust storms, which produced hazardous air quality categories across portions of West Texas and eastern New Mexico, are a preview of an emerging air quality problem that the regulatory framework is not currently configured to handle. The framework was designed for industrial air pollution from point sources, power plants, factories, refineries. The framework was not designed for distributed, episodic, climate-driven air pollution from wildfires and dust storms. The infrastructure of regulation is, like the infrastructure of physical systems, calibrated to the climate envelope that was. The recalibration to the climate envelope that is, in 2026, has not been seriously initiated at the federal level. There are state-level efforts in California, in Oregon, in Washington, in New York, and in a handful of other states. The federal effort is, by any objective measure, lagging. The political environment in which the necessary recalibration would occur is, in March 2026, polarized in ways that make substantive policy action difficult to achieve. The bipartisan consensus that produced the Clean Air Act in 1970, that produced the Stafford Act in 1988, that produced the National Flood Insurance Program in 1968, does not, in any operational sense, currently exist for climate adaptation policy at the scale that the events now require. This is the policy gap. The policy gap is widening. The infrastructure is undersized. The regulations are out of date. The funding is inadequate. The political consensus is absent. And the events keep coming. I want to take a moment because the underlying drivers of the March 2026 heat dome are not entirely explained by what I have walked you through in the previous parts. And the honest scientific picture requires acknowledging where the uncertainty lies. Let me walk you through what the climate diagnostic community knows and what it does not know about the genesis of this particular event. What is known? The 500 millibar ridge over the south-central United States is, structurally, a downstream feature of a larger hemispheric wave pattern that includes a trough over the eastern Pacific, a ridge over the central Pacific, a trough over the western Pacific, a ridge over the eastern Asian continent, a trough over Central Asia, and a ridge over Eastern Europe. The wave pattern is a wave 5 configuration. 5 major wave troughs and 5 major wave ridges around the hemisphere, which is on the higher amplitude end of the operational range. The hemispheric wave pattern is, in turn, embedded in a North Pacific Sea surface temperature anomaly pattern that has been, since the fall of 2025, in a configuration that climate diagnosticians refer to as a positive Pacific decadal oscillation phase, with concurrent positive North Pacific mode anomalies. The pattern features cool sea surface temperatures across the central North Pacific, surrounded by warm sea surface temperatures along the eastern Pacific Rim from the Gulf of Alaska south through California and Baja California. The sea surface temperature pattern in the North Pacific is, by the dynamic theory of mid-latitude atmospheric response to oceanic forcing, expected to produce ridge development over the western interior of North America in the cold season. The mechanism, in shorthand, is that the warm anomaly along the eastern Pacific Rim enhances the convective heating in the lower troposphere over that region, which drives a downstream Rossby wave train that produces alternating troughs and ridges across the rest of North America and the North Atlantic. This is part of what is producing the heat dome, but the magnitude of the heat dome, the 6.4 standard deviation departure from climatology, is not fully explained by the North Pacific forcing alone. Other factors are contributing. What is partially known? The role of soil moisture feedback, which I described in Part 7, is well established and is contributing significantly to the magnitude of the surface temperature anomaly. The dry antecedent soil moisture across the affected region is accentuating the surface response to the upper-level ridge pattern. The role of stratospheric polar vortex behavior, which has been in an unusually variable state during the 2025-2026 cold season, is potentially contributing to the persistence of the mid-latitude wave pattern. The polar vortex during the winter underwent multiple disruption events, including a major sudden stratospheric warming in late December 2025. The downstream effects of polar vortex disruptions on tropospheric weather patterns can persist for weeks to months after the stratospheric event. And the current Wave 5 configuration is consistent with the type of pattern that often follows a major sudden stratospheric warming. The role of the Madden-Julian oscillation, which is in phase 7 or 8 as of mid-March, is consistent with enhanced ridging over Western North America. The MJO contribution to this week's pattern is real, but is one of several factors, and is not by itself sufficient to produce the observed magnitude. The role of background anthropogenic warming, as I described in Part 6, is contributing to the magnitude of the surface temperature anomaly. The same dynamical configuration in 1980 would have produced a less extreme surface anomaly. The warming has added approximately 1.5 to 2 degrees Fahrenheit to the peak temperatures on top of the dynamics-driven anomaly. What is not known? The relative contributions of each of these factors to the magnitude of this specific event has not, as of this video's recording, been quantified. The formal attribution analysis, when it is published in the coming months, will provide quantitative estimates of how much each contributing factor contributed. The current state of the science is that we can name the contributing factors, but cannot, at this lead time, give precise percentages for each one. The question of whether the hemispheric wave pattern itself is becoming more frequent or more amplified as a result of anthropogenic warming is contested in the scientific literature. The quasi-resonant amplification framework that I described in the previous video on the June outbreak suggests that the answer is yes, that Arctic amplification is producing patterns more susceptible to high-amplitude, slow-moving wave configurations. Other researchers have argued that the case for a robust trend in hemispheric wave behavior is not yet fully established. The debate is active in the peer-reviewed literature in 2026. The honest scientific picture is therefore that we know enough to say, with high confidence, that the magnitude of this week's event has been increased by anthropogenic warming. We know enough to say, with high confidence, that events of this magnitude have become more frequent over the last several decades. We do not know enough, in our current state of understanding, to say definitively that the specific large-scale dynamical configuration that produced this week's event is itself becoming more common as a result of warming. Although the available evidence is increasingly supportive of that conclusion. This is the kind of uncertainty that the scientific community has to communicate honestly. The uncertainty is not an absence of knowledge. The uncertainty is a precise statement of what is and is not yet quantified. The cosmic forecast does not, as a channel, sell certainty where the science offers uncertainty. The cosmic forecast does, as a channel, distinguish between what is established, what is partially established, and what is actively contested. This week's event is, in the established category, an extreme heat event made more likely and more intense by anthropogenic warming. The exact percentage by which it was made more likely will be quantified in the coming months. The broader pattern of which it is a part is, in the partially established category, increasingly being linked to large-scale dynamical changes that may themselves be products of the warming signal. The science will continue to refine, the data will continue to accumulate, the cosmic forecast will continue to translate. I want to take a moment with the human dimension of the operational forecasting community. Because the work that the National Weather Service forecasters and the Climate Prediction Center diagnosticians and the Storm Prediction Center analysts are doing this week deserves to be acknowledged. The National Weather Service operates approximately 122 weather forecast offices across the United States and its territories. Each office is staffed continuously, 24 hours per day, 365 days per year. The forecasters work in rotating shifts. The shift pattern in most offices includes day shifts, evening shifts, and overnight shifts, with occasional double shifts during major events. The forecasters in the offices across the south-central United States this week, at Brownsville, at Corpus Christi, at San Antonio, at Austin, San Antonio, at Houston, Galveston, at Lubbock, at Amarillo, at Midland, Odessa, at Norman, at Tulsa, at Wichita, at Topeka, at Kansas City have been working since the heat dome began to organize last week. In continuous coordination with the Climate Prediction Center, with the Storm Prediction Center, with the Weather Prediction Center, with the National Centers for Environmental Information, with the regional emergency management agencies, with the state climatologists, with the agricultural extension services, and with the public. The workload is enormous. The forecasters issue, in addition to the routine daily forecasts, the area forecast discussions that translate the technical forecast into the language that emergency managers and local broadcasters can use, the specialized products for fire weather, for aviation, for marine interests, for hydrology, for severe weather, and for any other operational customer who depends on weather information. The area forecast discussions this week from the affected offices have been notable for the precision and the urgency with which they have communicated the unprecedented nature of the event. The Lubbock office's afternoon AFD on Tuesday contained the following sentence, which I am going to read verbatim because the language matters and the language is doing work. The combination of all-time record high temperatures, severe drought conditions, and elevated wildfire and dust storm risk represents an extreme weather situation with limited historical analog for the second week of March. Limited historical analog. That phrase in an area forecast discussion is the operational meteorology equivalent of a flare. The forecasters are tired. The forecasters are running, in many offices, with staffing that has been reduced over the last several years, as the agency has dealt with budget constraints and recruitment challenges. The National Weather Service has, by the union's own reporting, several hundred vacant forecaster positions across the country. And the offices in the affected states this week are running with reduced staff while simultaneously dealing with the most extreme March in their office's history. The Climate Prediction Center, which is producing the diagnostic products that I have been citing throughout this video, the 500 millibar height anomaly fields, the sea surface temperature analyses, the soil moisture monitoring products, the drought monitor coordination, is operating with a small dedicated staff that has been, by similar budget pressures, under-resourced for the scale of the diagnostic challenge that the climate signal is producing. The Storm Prediction Center, which will be the focal office for the severe weather threat that follows the heat dome breakdown later this week, is in a similar position. The SPC forecasters who will be issuing the convective outlooks and the mesoscale discussions as the pattern transitions are the same forecasters who handled the June outbreak in the previous video, and they will be handling the events that follow this one. The work is unending. The forecasters do it anyway. The work is, by the NOAA's own analysis, among the highest return on investment activities the federal government performs. The $1.2 billion annual budget of the National Weather Service produces, in terms of lives saved and property damage avoided, approximately $30 to $40 billion in benefit per year. The return is approximately 25 to 1. The cosmic forecast exists, in part, to amplify the work that the operational forecasting community is doing. The cosmic forecast does not generate forecasts. The cosmic forecast translates the forecasts that the NWS, the CPC, the SPC, and the WPC are producing. The cosmic forecast brings the operational language into the public conversation. The cosmic forecast contextualizes the forecasts within the longer arc of the climate signal. Without the forecasters, there would be no forecasts to translate. Without the diagnosticians, there would be no diagnostic context to amplify. Without the operational warning system, the consequences of events like this week's would be measured in many more lives lost. The work matters. The funding matters. The staffing matters. The political support for the operational forecasting infrastructure matters. And the forecasters this week are doing what they have done every week, every month, every year for decades, walking the public through what the atmosphere is doing, what it is likely to do next, and what the consequences are. I am as a channel in their debt. The cosmic forecast is, every week, an attempt to repay that debt by translating the work into the broader public conversation. The work matters. I want to close now with the central thesis restated for this event. Because the thesis is the part I want you to carry away, even if every parameter and every analog dissolves from memory. The central thesis is this: the temperatures that are being recorded across the south-central United States this week are not, in any meaningful sense, a normal March event. They are not the routine return of a periodic warm spell. They are not the expected variability of a chaotic atmosphere. They are the signature of a climate system that has departed from the envelope that defined the experience of the previous several generations. The 500 millibar geopotential height anomaly that is sustaining the heat dome is, by the diagnostic metric, plus 6.4 standard deviations above the 1991 to 2020 climatological mean. The surface temperature anomalies are running 25 to 30 degrees Fahrenheit above the climatological mean across an enormous area. The records being broken across hundreds of stations are being broken by margins of 1 to 5 degrees. The records that are falling are the records that stood for 55 years. The event is, by every diagnostic measure that the climate community can apply, in the upper tail of the modern instrumental record, and is, by the best paleoclimate reconstructions available, in territory that has no analog in the past 2,000 years for the date. The drivers of the event are multiple: the Pacific Decadal Oscillation, the North Pacific Sea surface temperature anomaly, the hemispheric wave pattern, the drought-loaded soil moisture feedback, the stratospheric polar vortex history, the Madden-Julian oscillation phase, the background anthropogenic warming signal. Each of these contributes. The relative contributions are not, yet, fully quantified. The formal attribution will come in the months ahead. The provisional attribution, based on analogous events, is that the event was made several times to many times more likely by the warming signal, and was made 1 to 2 degrees Celsius more intense by the warming signal. The consequences of the event are unfolding in real time. The infrastructure stress on the electrical grid, the water utilities, the agricultural sector, and the public health system. The cascading impacts through the dust storm outbreak, the wildfire risk loading, the early season grid demand, the early season heat illness presentations, the early season agricultural disruption. The longer tail impacts on the cattle inventory, the wheat harvest, the corn planting, the water supply, the insurance markets, and the disaster recovery system. None of these consequences will be fully visible until weeks or months after the event itself, but the consequences are loaded. The chain is connected. The drought loads the heat dome. The heat dome loads the dust storms. The dust storms load the respiratory illness. The respiratory illness loads the public health system. The public health system loads the political conversation. The political conversation, in March 2026, is not configured to absorb the load. The infrastructure of regulation, of insurance, of federal disaster response, of grid resilience, of agricultural adaptation, of public health preparedness, all of these are operating against a climate envelope that this week's event has, again, exceeded. The window is closing, the floor has risen, the dice are loaded, the math has changed. These are not rhetorical flourishes, these are descriptions of the data. I want to leave you with the open question, because the open question is, in the end, the only question that matters. The question is this: what do we as a society do when the calendar becomes unreliable? We have built, over the course of several generations, an infrastructure of expectation. The infrastructure of expectation says that March in Texas means highs in the 70s, lows in the 50s. The infrastructure of expectation says that wheat is planted in October and harvested in June. The infrastructure of expectation says that cooling centers open in May and close in September. The infrastructure of expectation says that wildfire season runs from June through October. The infrastructure of expectation says that hurricane season runs from June 1 through November 30. The atmosphere does not consult the infrastructure of expectation. The atmosphere does what the thermodynamics tell it to do. And the thermodynamics, every year, are telling the atmosphere to behave in ways that are, increasingly, outside the infrastructure of expectation. The result is the cascading failure that this week is illustrating across the south-central United States. The grid not designed for March cooling loads. The water utilities not configured for March outdoor demand. The crop insurance program not pricing the March risk. The cattle sector not prepared for March heat stress. The cooling centers not staffed in March. The schools not aware of the March heat illness risk. The dust storm monitoring not budgeted for March events. The wildfire response not mobilized for March conditions. Each of these failures individually is manageable. Each of them this week is being managed. The grid is holding. The water utilities are coping. The cooling centers are opening. The schools are adapting. The dust storm response is improvising. But the cumulative failure, the failure of the calendar itself, the failure of the entire infrastructure of expectation, is harder to address. The calendar cannot be fixed by patching individual systems. The calendar can only be addressed by acknowledging that the calendar has changed, and by rebuilding the systems on a new calendar. The new calendar is not yet written. The atmosphere is, in 2026, still in the process of writing it. What it will look like when the writing is complete is not yet knowable. The current trajectory suggests a calendar in which March in Texas can produce June temperatures, in which June in the Central Plains can produce historic severe weather, in which September in the eastern United States can produce hurricane events of unprecedented intensity, in which November in California can produce wildfire events that, in the previous calendar, would have been impossible in November. The calendar is sliding. The sliding is not gradual. The sliding is, in many regions and many seasons, occurring in step-change events that individually are described as unprecedented or outside the climatological envelope. This week's heat dome is one of those step-change events. There will be more. The cosmic forecast cannot tell you with precision when the next one will arrive. The cosmic forecast cannot tell you, with precision, what calendar will eventually replace the one we have lost. The cosmic forecast can, every week, tell you what the atmosphere is doing, what the operational forecast says, what the scientific literature has established, what the unanswered questions are, and what the consequences are likely to be. That is the work. If you have been watching this channel, You know that we have covered the major events of the previous several months in this kind of detail. This March heat event is the latest in that sequence. There will be more. The cadence is what it is. Subscribe to the Cosmic Forecast so you do not miss what comes next, because the warm season pattern that is loading across North America in 2026 has, by the longer-range models, the potential to produce events that, when paired with this week's March heat dome, will define the 2026 weather year as one of the most consequential in the modern operational record. Drop a comment below. Tell me where you are watching from, what time it is where you are, and your honest take on the question that this video is built around, whether the calendar outside your window, regardless of whether it is hot or cold, dry or wet, calm or stormy, still corresponds to the month it is supposed to be. The answer, I suspect, is no. The answer, I suspect, is that we are, all of us, living through the rewriting of the calendar in real time. The math has changed. The thermodynamics are not negotiating. The dice are loaded. The window is closing. And the heat dome over the south-central United States this March is the next data point in a sequence that, taken together, tells us a story we are not yet ready to hear. Stay with me. Until next time. The Cosmic Forecast is the place where the data, the mechanism, the historical context, the operational language, and the open questions get translated for everyone who wants to think clearly about what the atmosphere is doing. The forecasters are doing their work. The diagnosticians are doing their work. The climate scientists are doing their work. This channel is doing its work. The question in the end is what work the rest of us are doing. The window is closing. The clock is ticking. The next event is loading. What we do with the next 48 hours, the next 48 days, the next 48 months is up to us.